I'll do that. So officially, our last Thursday, our last class. It felt like about 10 minutes ago that the semester started for me. It's just flown by. So I will spare you all the usual, oh my goodness, I can't believe it's finals week already, but that's where we're at. Let's see, need to share screen briefly. I wasn't going to do it for the whole time since we all have, you can open up the formative assessment that we're going to discuss separately and have that to refer to, but for the recording, I have to have something open. I also, let me see, where is the share button? Here we go. There we go. It's like I've never done this before. I wanted to give you an update on how things are going with respect to your course evaluations. So can you see our status? Yep, we are at 4 out of 9 right now. So I believe the university evaluation closes on Saturday night, if I remember correctly. Hang on one second, I'm missing. Now Zoom doesn't want to show me all your faces. I love it when it fights with me. There we go. Now I got you back. Good deal. Okay, so university course evaluations close Saturday. Qualtrics closes next Wednesday if you want to do that. And there we go. Back to the share. We have then on tap several questions in Formative Assessment 7 designed to be kind of a wrap up, clear up remaining things that you want to talk about or things that you think we haven't talked about. A few folks mentioned, like, I don't remember talking about this, so we'll make sure that we try to hit as many of those as possible. So, this TAs, by the way, Erica and Vladimir were the ones who created this activity. And I was out of ideas and I was like, what are your ideas? What do you think would be useful? And they immediately stepped up and gave me these. So full credit to them. I was going to let them do sort of the lion's share of the guiding, and I would chime in periodically. So if you just want to have Formative Assessment 7 open, if you want to refer to the wording, I'll have it as what's the video that's being captured as per usual. So let's see, Erica, did you get your microphone fixed? And I see, yeah, other folks are having technical difficulties too. Can we start? Okay, we'll go out of order. Vladimir, she wants you to start while she figures out what's going on with her laptop. Which one do you want to talk about? Were you doing question 3?
Yeah,
The story
let's
problem?
yeah, I think so. And sorry for the long story. Blame me, not Lisa, but I think the answers were amazing. I really enjoyed reading your answers. So thank you for taking the time of describing what you thought. And yeah, I have a couple of questions for you, more than answers. So tell me, Lisa, how do you want to proceed?
Can we give them about 30 seconds just to reread the question?
Yeah, of course.
You can't see your answers. Well, that's great. Let me see if I can fix that, because you should be able to see your answers. I believe that is a setting on the quiz itself. One moment. Okay, so yes, I was going to suggest we spend just like 30 seconds rereading the question so that we're all familiar with the story.
Do you want me to read it or?
I was going to let them just read it to themselves.
Yeah,
Unless you want to. You can practice your, voice acting.
that's a lot, but I can give you some context about the question. Uh, but you can read it first, so then we can talk about how I thought about this. Thank you.
All right, is that good? Oh, we good to go? All
I
right,
think
and
so.
Erica's back. Welcome.
Question 3, Mike.
Yeah, we were going to start with that one since Erica was having technical difficulties, but she's here. We'll see if she sticks around.
Hopefully, yes.
The internet can be fickle sometimes, so I won't take it personally if you're like, zoom.
Okay, so do you want me to start with question three?
Yes, please.
Okay, so uh, the idea for this question, when I read Lisa's email, I was thinking about how to translate the things that we have learned in class into practical things. And I know that we already had case scenario for one of the formative assessments, but in this case, I was trying to reflect some of the things that I've experienced in practice working with people in a research center and now working as a research assistant with some people. So the idea here was for you to try to think what kind of things you would say and you would do when you have to help someone else. And I've also found that this is helpful when we have to explain something that we want to do. Especially, for instance, when we had my comms exam and the master thesis defense, I had to answer some questions like, what would you say? How would you explain this? What would you do under these circumstances? And I think that those kind of questions are very helpful to try to think from another perspective, because I know that we have learned these things, right? We all know what a within fixed effect is, what a between fixed effect is, and what are the differences between a contextual fixed effect. But those things are like understandable now that we have been studying this for 4 months, but that's not something common for other people. So that's the context, and that's why I thought about a scenario or case in which you could describe what would you do if someone, for instance, colleagues, are interested in conducting research in some educational settings and they have nested data, because clearly this is nested data. And as you read, the case is based on how some student level attributes are related to an individual outcome. In this case, we could have something like 3 levels, but I also read one answer that proposed something like a cross-level model at level 2, something like a cross-classification model, because we don't know if all the schools are in the same state and if all students in the same state attend to the same school. So I found that's interesting. But for now, you know that we have a 3 level data potentially, but we are interested in student level characteristics. That being said, I think that your answers were great. Many of you mentioned that you would analyze the outcome, the predictors, the variability at level 2. Many of you said that you would work with a 2 level model, although I didn't read how would you do with level 3, because remember that one thing is statistical significance and other is practical significance. We know that with something like 10 units at any level 2 or 3, that's almost nothing, right? But it doesn't mean that what we have there doesn't matter in the model. So we must make some decisions. In this case, if you are interested in a level 1 thing, you could even think about how to fit a model that answered the research question. That's another interesting thing that I thought when I was reading your questions, because many of you were like, okay, I have the data, I would do this. But if you read the case, this thing is, how would you do? How would you help your colleagues to conduct this research? So I think that for many of you, this was something like, if I would have this data and I should have to answer this research question, this is what I would do. Although I was thinking about how would you translate some of the things that we have learned here into simple words, into simple words. Uh, and that's interesting too, because many of you went to the model immediately, um, without considering that maybe the research questions could be different and the models could be different once we have a first approach to our colleagues. Um, so I have one question for you, because again, I think that your answers were great. Many of you mentioned the ICCs, the within versus between effects, things at level 1, things at level 2. Some of you mentioned the idea of pseudo R-squares instead of the regular R-squares in linear models. And you also mentioned why a multi-level model would help here. So good job. One of the things that I was interested in when I wrote this, it was the difference between random slopes and interactions in our models. And you can see almost at the end of the example that I mentioned something like the researchers, let's say, wanted to explore potential variations in the gender gap in performance between schools by adding interactions to the model between biological sex and school variables. Yes, for formative assessment 7, question 3. So one of the questions that I have for you is, for you, what's the difference between random slopes and interactions, and what would you think they are doing in our model? Why would you add a random slope, and why would you add a cross-level interaction? What's the idea behind those two things? Do they complement to each other? Something like this, something like that. Sorry, what do you think about that? Because what I read is that you were mentioning we should do this, this, and this, but what's the reasoning behind that? That's what I would like to hear from you.
And no one wants to talk, but I'll phrase the question slightly more directly. Why, like the first step is to explain to the researcher why they can't just use the regression, right? And then it's like once you get into that, like, no, we need multi-level. Why? And then like what flavor of multi-level do we need? Like, and I think that's where Vladimir's going in terms of what do random slopes do? How do they map onto the question? What do cross-level interactions do? How do they map on? So I think they're like, it's always your job as a methodologist to help teach the people that are coming to you for help so that they can recognize when situations occur in which they need help. So I'll just put that into the chat there.
Yes, thank you, Lisa. What would you say?
Yeah, so in my case, I think I was talking about looking at the variation in gender gap across school by using like a random, using a random slope. Yes, because I'm thinking we have too many schools to be able to say that we want to look at the interaction between each schools specifically that we have. And with the multi-level model, we can know how that gender gap varies across schools by using a random slope rather than an interaction. But I'm thinking if I have two schools, I think an interaction with the two schools will be the same, will give the same information. That is what I'm thinking.
About random slopes and interactions, you mean?
Yes, so the question is about gender gap across schools, right? And we have schools in this model as a level two, thing. And we did that because we know that we have about 50 schools. So we won't be able to use the schools like a fixed effect, such that we'll be able to do an interaction between gender and the schools themselves. But I'm thinking with the random slope, it will still give us the variation across schools. Even given that we have up to 50 schools, we'll still be able to say that this is how this varies across the schools.
Yeah, agree. And I like that because the idea is if they were interested in something like variation across schools in the gender gap, we know that a random slope could help us with that, right? The random slope would tell us that the fixed slope of the level 1 predictor varies across schools at level 2. That's one thing. The other thing is what kind of school attributes could help us to explain or analyze that variation at level 2. And that's why random slopes and cross-level interactions, they complement to each other. They are part of the same story, and that's why most of the time, as a prerequisite of cross-level interactions, we test random slopes, because we want to see if part of the variation we find in the level 1 slopes across clusters can be attributed to any level 2 or cluster attribute. So they work together, and both are trying to help us analyzing variability across clusters. The thing is, the cross-level interaction help us with the why part. First
Yes.
of all, we should identify something. But remember that this is a question. Yes, question. Can we have cross-level interactions without a random slope for our level 1 predictor?
Yes, I believe so. I think that is what we
Yes.
usually call the systematically varying effect.
Exactly. Yes. So that's the thing. Even if our level 1 predictor doesn't have a significant random slope, we could add a cross-level interaction, because we can assume that after adding that cross-level interaction, our level 1 fixed effect doesn't vary across clusters. So it is systematically varying based on the level 2 attribute that we included in our cross-level interaction. Now, other thing that Ray was missing is missing data. I think that only one student mentioned that, one or two students mentioned the relevance of missing data here.
Interact real quick. Can
Yes,
I ask what a systematically varying slope, like what pile of variance it would explain before we go to missing data?
good question.
Because if we have the cross-level interactions explaining the random slope variance, but then we don't have the random slope. Yeah.
I don't know. What, what do you think?
I'm playing charades. I'm illustrating your questions.
Yeah, I appreciate it. I mean, what variances would we have in the model if we don't have a random slope variance? Like,
I think it will probably affect probably both the residual variance at level 1 and also some from the level 2 variance as well. That's my thinking because now it goes both ways, so I'm not sure.
so we would, yes, we would have the random intercept variance and we would have the residual variance.
Okay.
We would have those left, but we pull the random slope variance out of the residual variance. So if there is no random slope variance to explain, it's going to go back to that residual variance. But yeah, it's a trickier thing when you have the fixed effect in there to explain the variance, but the variance is not there for that fixed effect to explain it, so it defaults back to the residual.
Yes, exactly. I agree. So that's tricky as you said, and in my experience, I've not seen that yet. Most of the time, the level 1 things that I analyze have systematic variance at higher levels. But I don't have an example about a systematic varying level 1 thing across clusters, but for sure there may be some out there. So now, is that clear? That idea that Erika mentioned? Are we good with that? I would say yes. Okay, if you have questions, please just raise your hand, or you can open your mic. So now going back to the missing data thing, what do you think about that? Would you do that in practice? Would you advise that? Yes, let me rephrase myself. Would you advise removing missing data like the first thing? What could you say about missing data?
First, it depends on how you're analyzing it, what the data is. I mean, with this particular data, you might be able to be okay using the missing data and using the I'm trying to remember the correct terminology. Imputant? Is that right?
Yes,
Impute.
Yeah,
Yeah.
yes.
yeah. And maybe throw in the means, where maybe it's missing or something to help out with the your calculations. But um, I would also like to see how many of your responses have missing data. Because if a majority are missing data, that would make that method really not very good. But if it's only a few that are missing, that would probably be okay. Or if it's only a few, like maybe 20 out of 10,000 or 2,000 or whatever, then I think you could remove those and you'd be safe to still have a very good analysis.
Okay.
And one thing, I'm not sure, do we have missing data in this specific example or we are just talking about? I was thinking, I don't think I see missing data in the description.
Oh, yes. I didn't include the specific details, but we have. That's why our colleagues would remove those missing cases as part of the data preparation.
Mm. Yes, I think I agree with some points Mike already made on the fact that depending on the volume of the variation or of the missingness, we can be okay with removing those observations and doing the analysis as it is. But one thing I'm also really like with missing data is creates more problem. Like, how you are going to be confident to say that it's missing completely at random or missing at random, those kind of decisions, right? And I think we'll need to investigate how some of the missingness relates to other variable first to be able to make that kind of decision, right? So if we see some pattern in the missingness, so definitely is not going to be missing at random. And for example, the multiple imputation is assuming that it's missing at random. But I know that there are some other imputation method where you can use the observations that are not missing to predict what the missing values would be. And depending on what you find, that might be a better approach than just doing a random multiple imputation.
Yes, thank you. Thank you for introducing some terms. And let me ask you something, because my intention here is not talking about missing data methods. We had a course about that last semester and was amazing. Uh, Jonathan's taught many things about missing data methods, but I don't want to go that deep. But let me ask you this, because in this course, I'm sure that you have heard, maybe you remember that we have said something like, when we use maximum likelihood, we can work with missing data, but we work with the missing at random assumption. Okay, so maybe that's something that you would say to your colleagues. Don't worry about missing data, because you can work with it if you use maximum likelihood, because you will be working under the assumption of missing at random. How would you say that in simple words? That's my last question for this activity. How would you say that? How would you translate that into simple words? Because to me, that's something like I have in my mind. It is like, what's in a generalized in a binary logistic regression model? What are we doing? I already have in my mind, we are predicting the log of the odds of the probability of a one, right? Things that we have in our minds. If you work with maximum likelihood, don't worry about missing data, because you will be working under the assumption of missing at random. How would you say that in simple words? Or how would you explain that to someone outside our class or field? Thank you, Lisa. Please check that if you're interested in missing data methods. What do you say? That's my last question for you.
I would jump in and say I would not say that it handles missing data.
Yes. Yes, we are not handling missing data. You are muted, Lisa.
Local mic was muted, sorry. Why would you not say handle?
It's vague and it doesn't explain anything. It seems like you don't know what you're talking about.
Handle is a word that people use when they don't know what the right word is. So you will see that missing data is handled. There's other, like, dependency is handled by multi-level models, that kind of thing. So, yep. I will say, can you just do standard multiple imputation software on a multi-level analysis? No, that's the other part of it, is that your imputation model has to match the analysis model. And so that's where the problem comes in with missing predictors in multi-level models, especially, is trying to build an imputation model that would anticipate all of their fixed and potentially random effects. Because anything you don't put in the imputation model, you're not likely to find in the analysis model.
Yes.
I have a question before we move off. So in the case you wanted to try to do that, would you first maybe try to fit a model after you removed, the data rows that have some missing data, fit that, and see how well they predict those values in the rows with the missing data to see if they do relatively okay-ish? Um, or would you just not even try?
I can answer that. I think based on Jonathan's course, there are many options, Mike. The thing is, let me simplify this. There are like, you have like two options. There are two branches. One is you have your specific model. So you try to recreate your missing data using that model as a reference with the outcome and the predictors and the auxiliary variables you have. So in multi-level modeling, that's essential because remember that level one and level two things for the same predictor at level one can be different things. So if you specify your model, your target model, you can get predictions for your missing data based on the model, but that's hard because we know that we not all the time we have our full model. We are like chasing interesting things. That's one option. The other is like a naive approach in which you use those variables that you think will be relevant, and you have your auxiliary variables, because auxiliary variables are slightly different than your predictors. They are things that help you to understand what the missing data pattern is. Okay, but they cannot be part, they don't have to be part of the analysis necessarily. But from the naive approach, you have a model too, but it's general. You impute your missing data and then you conduct your analysis. In both cases, I think that then you will need some way of, it's not merge, pull your results, because it is not only one imputation. Most of the time we use multiple imputation, which means we have different data sets with different imputed missing data values. So then we must find a way to pull those data into some estimates that we can use as if they were the final model results.
So, Vladimir, is that the end of your list of what you wanted to say for this question?
Yes, for question 3, yes.
Okay, Erica, do you want to add anything?
I was just gonna say, like, thinking of pooling it and having multiple like versions of the multiple imputations kind of reminds me of Mubarak's project with like the different predicted scores or whatnot, where he had to pool these different values and handle it by having different values for each student. So if you think of it like that, similar kind of concepts.
Yeah, it actually is almost identical in terms of
Yeah.
like the logic of it, because when you do an imputation, you're predicting a point based on a model. So like the fixed effects say this missing data should have been here, but you don't plug that in. You add some kind of random residual to it, so you're sort of plugging it around the line. And plausible value is each plausible value is then like one version of the truth, essentially, because in factor analysis, the mean factor score for a person is kind of like the multiple imputation value hitting exactly on the line. And then rather than just saying, well, I'm only going to use the mean, you're going to use the mean and the standard error to create a distribution for each person and just make plausible value draws out of that. But then you got to put it together on the back end. And you can't just analyze like a combined data set of plausible values. You have to analyze each separately and then pool the results. And there's rules for that in pooling plausible values, the same rules that are used in pooling missing data imputations. So I think that's a fairly useful approach. Bayes sort of makes it unnecessary, I think, because then you have all these draws rather than just like the 5, and the analysis and the missing data are sort of like they work together like in a sequential manner rather than missing data in one step and then analysis in the second. But yeah, that's a whole big thing. I wanted to add some questions to this. So, based on the commentary we've had so far, we have three levels potentially of this analysis. So, we have level 1 students, level 2 schools, and then level 3 districts. So 10 at level 3 is not enough to make a level, meaning to estimate a variance across those 10. It's not going to go well. So I would agree with a fixed effect strategy in which essentially you treat district as a categorical predictor. You put that into the model for the means. It soaks up all the district level mean differences so that you then don't have that source of dependency. 50 schools, though, you get a choice. I think in terms of the story here, because they wanted to see what school characteristics predicted student gender gaps, that lends itself to treating schools as random, meaning estimating a variance across school mean differences and potentially having slope differences across schools too as the random slope. And if you want to know why some schools differ from each other in their means or they differ from each other in their gender gaps, that lends itself to main effects and cross-level interactions with level 2 predictors. But if you don't want to know why, you just want to know what. So, for instance, if I were the manager of a district, right? I'm the superintendent or whatever, like the head person is. And I want to check on this. Like, I want to know if there's a gender gap at Wickham Elementary or this other elementary or this school or this school. And I want to be able to report, right, to parents and teachers that this school is equitable. See, our gender gap isn't any bigger than the other schools. Then that would merit treating school as fixed, as a categorical predictor, so that you can make specific conclusions about the gender gap in this school, in this school, in this school. But it wouldn't allow you to predict why they're different. But then the intention is different in that case. So that is allowed. In terms of the motivation here, I want to tell you a story. I think I've told you this story before, but it bears repeating. I once listened to a job talk where someone had a 3-level design like this. And that person started out using multi-level models, she said, and none of the school or district level predictors were significant. And so she thought that gave her a license to go back to multiple regression. How do we think about that? Cool or not cool?
I would say not cool.
Not cool. Why
It
not
just
cool?
means that you don't have the things to explain the variation at those levels. It does not mean that those levels do not exist. That's what.
Exactly. It's like just because you don't know why the dependency's there doesn't mean it's not there. And what happens if we ignore dependency? Like, why, how, and in what way would the results be wrong? Like, if this researcher in the story stuck with the original plan, what happens to the quality of their results, we'll say?
But remember, I think this will bias the results such that, for example, the test that we are also doing, the standard errors will be wrong. Therefore, when we are saying something is significant or not significant, it is based on those standard errors. And if those are wrong, pretty much the conclusion is wrong as well.
Mm-hmm. So standard errors are going to be some flavor of wrong, and they could actually be too big or too small, depending on how the model is misspecified and at what level the slope is. What about the slopes themselves? We put in gender, we give it a main effect, we make some interactions between gender and school, whatever. What's wrong with that? Oh yeah, I'm missing a golden opportunity right here. This smushing. Yeah.
Yes.
There is another approach that we haven't talked about in this class much that you will read about, and it is cluster corrected standard errors. Like, this is a thing you can do very readily in Stata, for instance. And a lot of folks say, well, if you don't care about your nesting, like you only care about your students, then you can just do cluster corrected standard errors, and it's fine because then your standard errors are correct. But then what about the slopes? So if you do a cluster corrected standard error, then you have an accurate standard error for a smushed slope. Not better. I would say not better. Okay, last question. So gender is binary in this story, Vladimir, is that right? 0, 1? Okay.
Yes, it is.
Okay, and we need a random slope for gender, right? So that we can test cross-level interactions and see how much of the slope variance is explained by school things. Can I put in the 0, 1 version of gender as a random slope? Cool or not cool? You can do thumbs up or thumbs down. Cool is thumbs up. Not cool
I
is
think
thumbs down.
you can, but you would want to center it based upon a percentage in a school for like what for your within cluster centering, as opposed to just based off of the 0, 1, if I remember correctly.
If you're talking about doing cluster means centering, then yes, yeah. So
Yes.
you would need to subtract essentially the school level variation in gender composition to isolate what would be the gender gap in a school, controlling for how many of girls and boys there are in the school. So yep, and that is something that I only learned recently. So this is a problem that you will see in the literature, I think, with greater frequency. Which actually I think is a nice segue into, let's go backwards to question 2. Because you're going to be reading multi-level analyses. A few of you have made comments to me that you feel hopefully more capable of understanding methods and results sections using multi-level modeling. And so to be a competent consumer is an excellent objective. So when you're reading other people's results, what are your indications? So Erica, this is your baby?
Yeah, I mean, we did kind of talk about it before, but I know it's a lot harder when you're actually reading articles in practice and you're like, okay, yeah, I'm taking this as it is, and then you're not being critical, and then you're like, oh wait, something's wrong here. I remember something that Lisa told me, and I should be critical of this. So what are some of the signs that you would look for or you have seen?
I think we've talked about when they are talking about level 1 predictors, and then they are explaining both level 1 and level 2 means. And I think in doing some literature for my class projects, I actually saw something like that where they are saying we want to include student characteristics alone, and then want to include, they are doing like kind of sequential analysis with just student characteristics and then with school characteristics. But then I'm looking at the result for the student characteristics. They did not explicitly state that, oh, we have the student level version of this and the school level version. They just included student characteristics as one variable. And then they are saying we explain level 1 variation and level 2 variation. I'm like, yeah, you would explain that because it is smushed, but they did not explain why they were able to, they did not say why they were able to explain level 2 variation when they are just including level 1 predictor in the model.
Yeah, no, that's a really great example to say like, yeah, we're just including like level 1 variables as is, and yeah, you see like both the residual and the random intercept variance being explained. It's like, okay, this is clearly accounting for both. So that one is definitely helpful in looking at yeah, like the tables of what they report, the effect sizes. What else? Where's anything you came across? I'll also say it's, in my experience, a lot easier when we're just talking about like observed and continuous variables. It's a lot easier to be like, okay, we're looking at level 1 predictor, yeah, like a student characteristic, and then looking for the level 2 slope. But once we get into like MSEM or SEM, which I know we didn't get into, but you'll likely see if you're seeing other related literature. And Lisa has materials on it so you can reference if you're looking. That is a lot more complicated to see when they're smushing or not because the latent side of it, it can be a little bit more confusing. And yeah, and not saying like if they cluster mean centered or grand mean centered or like the I think situation that Lisa was kind of hinting at earlier of thinking of having a grand mean center variable, so like a binary that you predictor that you put in as is, and you try to make a random slope out of it, you're going to get your smushed random slope. So then you would have to add in the random slope of the level 2 part of it, but then as Vladimir well knows from his master's thesis, it's not going to work well. It's weird, and it's not going to work well to add a random slope for the level 2 part of that variable. So you get into those more weirder cases, it gets more confusing, but definitely would say like figuring out the sampling design that they're talking about, seeing how they refer to like the dependencies, if they're checking ICCs, if they're mentioning centering that they did, check that they did the centering that they say they did. And yeah, looking at the results to see how many slopes for each level, looking at the effect sizes, stuff like that.
I concur. I'll add another one. When people are talking about slopes using 1 unit higher language without saying higher than what. So if you have a level 1 predictor and a level 2 predictor of the same variable, then you have to be very careful. This is like a student who is higher than the rest of the students in their school by 1 unit, this is their change in their outcome. For schools that are higher than other schools by 1 unit, this is the additional change in their outcome. So I think just interpreting slopes without references as to higher than is also a giveaway that they're not thinking about it in terms of separate levels of analysis. I'll add another one to this. Let's say that at the beginning of the method section it says, well, students were sampled from schools, but the intraclass correlation was only 0.04. And I read this article once that says if it's under 0.05, it's fine, and I can ignore it. So that's what I did. Cool? Not cool. I see thumbs, I see head shakes. Folks who haven't spoken today, why is it not cool?
It's so cold outside.
So you're going for the literal interpretation. Fair enough. It's not as cold today. No, is there a level of ICC at which you can say, no, it's totally fine, I can ignore this? Yeah, 0. Yeah, Robert, what do you think?
Well, yeah, I was going to say, technically it would only be if it's like exactly 0, right?
Mm-hmm. The other part of it is what happens to the random intercept when residual variance is explained at level 1 by like people things. What happens to the random intercept if residual variance is reduced? Yeah, it goes back up. And if your random intercept variance is higher than it was to begin with, then your conditional ICC could be well above the golden 0.05 standard. I've seen that in longitudinal data fairly frequently. Once you control for like change over time in terms of linear or nonlinear slopes, like that will soak up a whole lot of the residual variance, and it will make your intercept variance and your conditional ICC much higher. So yeah, I don't think there's a value of ICC that's safe to ignore, maybe not even exactly 0, because it may not stay 0. So in that situation, I would probably leave the random intercept in and watch it as I add things to the model. If it's always 0 and it stays that way, then I think you can feel pretty good about my results are not going to change based on this. But otherwise, you wouldn't know unless you look for it.
Yes, I have a question regarding that. I think from some of the readings I was doing, I see people report ICC across the levels of. So, for example, the people doing sequential modeling, as they were adding variables at each level up to the point where they have the final model, they were still reporting ICCs across. I cannot remember the pattern, maybe it's increasing or decreasing, but what I was thinking when I was reading that is the variables we are including supposed to say something about the ICC? Are we supposed to say the ICC gets bigger or it gets smaller? I don't know. So I'm like, why are we reporting ICC when we are including each of those variables, and what do we want to get out of it?
I do not do that. And I don't think it makes a lot of sense. So the interclass correlation in an empty model is designed to tell you how much of the story is your cluster versus your person. let's say in this context. Like, then you add stuff to your model. So your ICC could become bigger because you've done a good job explaining student variance. It could get smaller because you did a crappy job explaining student variance. Like, the ICC of what's left is a function of both how much was there to begin with and how effective your model is at capturing it. And so you can get different ICCs because of different levels of effectiveness. To me, that sort of confounds the point of the ICC. It's the amount of dependency essentially in what's left over, and what's left over is going to be a constant shape shift as you add things to the model. So I have seen that. I don't think it makes a lot of sense.
Okay, I was thinking it doesn't make sense too. I'm like, maybe I'm not understanding what they are trying to say. Thank you.
And also, I will still die on the hill that random slopes do not explain variance, and that makes zero sense too. But you will see people report an R-square after adding a random slope, and I do not think that's cool. If you go from a model with just a random slope and a residual to one, or random intercept and a residual, to one that has a slope, as Erica said earlier, the slope variance is coming out of the residual variance. So the residual doesn't have the same interpretation because you've sucked out part of it and given it a separate name and put it in a separate level. But also, the random intercept does not have the same interpretation either, because it is specifically cluster mean differences at the 0 value of the predictor the random slope is for. So then it's a different random intercept than it would be if it's not conditional on any random slope predictors. So to me, like, it's apples and oranges when you go from a 2-pile model, so to speak, to a 3-pile model. Like, the 3-pile should be the new baseline, because you're keeping the variance part constant and seeing what happens as you add, say, cross-level interactions that would explain the random slopes. So the sequencing to get R-square is kind of tricky, but I think that, to me, it doesn't make sense to go back to the original empty model once you have random slopes in the story.
I would just add that, like, we've seen before the photos of, like, when we have random slopes and they're all going their different directions and how we move the intercept, like, that's what Lisa's talking about. Like, if you think of it visually like that, where it's like, yeah, it could be like a lot of variance on this side, but on this side they could all be really close together. So
yeah, a random slope necessarily implies heterogeneity of variance in a parabola shape across the predictor the random slope is for. So if you picture like a butterfly almost, there's going to be a point at which the variance is a minimum, and as non-parallel lines, right, eventually cross, the further out you go, the higher the variance is. So if your intercept's out here, that's a different depiction of which clusters are high than like if it's over here or even in the middle. So it's not comparable in that sense, I would say. Yep. Other thoughts, questions on this topic? And yes, each of us needs to be our own peer reviewer. Just because it's published in a good journal doesn't mean that it's right. What that means is that one associate editor and probably 2 reviewers said it was good enough. And if those 3 people on Earth didn't know about some specification, then it's going to make it into the journal. So there are excellent papers that are not published. There are crap papers that are published, right? We all have to come and make our own evaluations. All right, question 1. Do we want to move on? Now this one, I read the answers and there was a lot of variability, I think, in this. So this is yours too, right, Erica? Okay, take it away.
yep, yeah, I got 2 short ones. So I thought that, like, a lot of you came up with like a lot of different responses, but had a lot of thought behind your responses as well to thinking about, because just giving an estimate and a name is limited information. So I thought that you asked a lot of important questions, because you don't know, like, is the variable continuous? Is it like categorical? Because that's important. I would say that, like, in terms of like the notation, like, the intention was to have within cluster stand for the WC, and then cluster mean with CM, so that they would be the cluster mean centered. So I think I saw some of them like not understand that. So just in terms of the notation in that. But yeah, so if it was a continuous variable, I know a lot of you got like the per 1 unit increase, it goes up this much for just the main effects. And also, as Lisa mentioned earlier, thinking of the reference of beyond the like kids' school that they're in, their cluster mean of that school in that variable of like 1 unit beyond that within the student. And when we're looking at the within cluster, because we have to reference the school mean. So I thought that was obviously an important thing to notice. Like it's the same variable like you would get in the data set, but obviously we have to separate it to make the two slopes, to put it in the model to unsmush it. And then we get to the fun part of the cross-level interaction, which I think is the most interesting. Um, so I would just say, like, if we're thinking of a interaction that you would get just even from like a general linear model perspective, when you get the actual estimate of like this variable times this variable, what is that estimate representing?
It's representing basically does the effect of, like, if you look at, how do I word this right? So if it's one variable interacting with another, and basically it's saying that the estimate of the interaction is saying, is the effect of one of the variables going to become stronger or weaker when it interacts with the other variable?
Yeah, I know Lisa's go-to language is like the slope difference of looking at the difference between the slopes is like what you're getting from the estimate to see from like one group to the other. And then yes, if we're thinking of like referencing how to interpret an interaction, if we're looking at like within cluster permissive and then the interaction term, like the interaction term is going to tell us whether or not it's making the within cluster or the clustering because they're both positive. But with all of them being positive, whether or not it's going to make it like more positive or stronger, or if it was negative, whether or not it would weaken the effect based off of that. But also, when we were thinking about it, if it was a well, because a lot of you like obviously understood that like okay, it's positive, it's stronger, which is obviously a good interpretation. I know interactions are not many people's favorites, except for Lisa's. I know I can't say anything. My thesis was interactions, so. But no, when we're thinking about this with continuous, it's a lot easier. But when we're thinking about it as binary, what is the difference of when we're thinking about just the estimate? Like even if we're just looking at the main effect, if this was a binary variable, what would that estimate be telling us? In terms of when we're thinking of like the 1 unit increase.
What I will say is that that's kind of like what I was working with my model. And when I was interpreting things, I did not like the idea of the full, that full change. Instead, I said, you know what? Let's just drop it down like Lisa suggested. She suggests 10% increments because that's a nice, quick, easy mental calculation. But if that did not work for you, maybe you wanted 5% increments or 20% increments or whatever, something that nicely goes into one to say, this is how much is changing over time as opposed to just this is the 100% change, and you're really not able to kind of visualize how things are changing from one to the other the way really you should be.
Yeah, exactly. No, it's kind of difficult to think of like, okay, within a cluster permissiveness of like zero or any variable of like not, you have absolutely no of it to absolutely all of it is like not as intuitive, and it make for interpretations as well as like if you were to just like move the decimal and yeah, turn it into a percentage to more easily say like as we increase instead of from 0 to 100 by like 10% or something like that to make it more understandable in that case. Yeah, but I do think that that was a really good thing that a lot of people noticed of like yeah, not mentioning what type of variable it is, and that's obviously going to affect the interpretation of whether or not it's the 1 unit increase means like 1 unit increase on the scale or 1 unit increase in like they have it, they don't have it. And then there's a special name for this type of interaction, not just being a crossable interaction. If bonus question. If anyone remembers what Lisa calls it, it's when like you have the within cluster version of the variable interacting with its cluster mean.
I think that's what she calls intravariable interaction, right?
Yes. Yeah. So it's like not just thinking, you're thinking of like the two parts of it, because yeah, being you yourself as a student in a school having certain amounts of permissiveness that could depend on whether or not you're in a school with certain amounts of average levels of permissiveness and vice versa. And so that's also important, just like even if you're thinking of that variable itself, you have your main effects and your interaction to look at like the different versions of that variable as it is instead of, you know, just looking at the main effects and seeing if within cluster mean only.
You want to make them do the numbers because only a few people actually put the interaction term into a sentence.
True. Anyone want to try the challenge?
Put 0.42 into a sentence. That's the challenge.
Be brave. Yeah. Yeah, because you got the stronger part correct.
A, you're smiling. Are you feeling confident today? Like, nope, I'm not smiling. I'm not happy. Definitely not. Michael's smiling. Do you want to try to put 0.42 into a sentence?
I will say 4-2 is somebody's favorite day of the year. Sorry. Let me bring up what I have here. For every unit of increase in student permissiveness, risk increases from school permissiveness increases by 0.42, and you can flip those around.
Can you say that again?
For every unit increase in student permissiveness, a risk increase from school permissiveness increases by 0.42.
Okay, the risk increase. So you're saying the slope for the cluster mean increases by 0.42. Yes, I would take that. Erica, what do you think about that?
Yeah, I mean, kind of going back to what we were talking about before of like the slope difference. I know, like we're thinking about the estimate and then adding on the slope difference. And I also think it's helpful to think of it like in terms of if you're asking for like linear combinations, if you want to see like the effect of like, you know, being in a school with like certain like the simple slopes, I think, right, Lisa, correct term, of like adding the within cluster permissiveness plus the slope difference to see like that simple slope, or the other way around. It's a lot easier when you think of it in terms of like, I think binary predictors, you know, when you're like yes, no, in terms of that case. But yeah, their slope difference, how much you're increasing beyond your original estimate.
Yes, I'm also trying to think about if you are trying to say this to a layman, because I'm thinking saying that there's an incremental increase of blah blah blah, permissiveness. I'm thinking that would probably be hard. I'm trying to see that, okay, if you are in a school with more permissiveness than the average school, that is how there is going to be higher risk for students in those kind of schools, right?
Yeah, I mean, it would be more helpful in interpretation to have it centered on beyond like cluster mean centering, centered on meaningful values, for like the cluster means, to think of like, okay, what are the average overall clusters? And then you can think about like within like a cluster or like between cluster differences, and to think about like, okay, yeah, what would be like a low level of permissiveness compared to a high level of permissiveness, and like thinking about also in terms of like plotting it, of like getting predicted values to see the different like
Yeah.
um, way the trajectories is a lot easier to understand. But yeah, thinking about it of like if you're student in a school and you have this level of permissiveness, and as you increase, your risk of the cyberbullying is going to increase. And then if you're in a school that as you increase your levels of permissiveness, that school overall, like the student's risk of cyberbullying is going to increase. Like I think really just trying to break it down to like as simple as you can, but and it can't be hard with all the words.
Yeah, I like to start with like a sentence that's a slope and then talk about what happens to it. So in this case, students who are relatively more permissive than other students in their school are more likely to be involved in cyberbullying. The extent to which that is the case is higher in schools where there's a lot of permissiveness. So it's worse. So then you can talk about like the within school effect is stronger to the extent that the school has a lot of this permissiveness happening as well. So it's like if you sort of layer your explanation, like get them to have the slope in their head and then add something to it that changes the slope is I found that to be more useful. And by the way, reviewers hate terms like more positive and more negative. They hate them. So that's more of like this is just a categorization system in your head as to how to approach the problem, and then you come up with like the GRE words that make more positive, exacerbate or those kinds of words. Or if it's less positive, that'd be like mitigate or something along those lines. Let me ask a question about choices here. So this is a cluster mean centered example. Is this model okay if we didn't do that, if we just put in the original student permissiveness constant centered somehow? Because we've got the cluster mean in there, right? So it should be fine, right? Cool? Not cool.
No. Oh.
No, not cool. No, what would we need to do to fix it?
We would have to include the interaction for the cluster means as well.
That's right. We would, whatever you do to level 1, you got to do to level 2. That's the rule when you're doing constant centered level 1 predictors. So that means we would need a CM by CM interaction to unsmush the cross level interaction with the original constant centered level 1 predictor. So yeah, getting this stuff right is very tricky. My preference is for this version of the model where everything is sort of sitting at its own level, and then if you leave something out, you're saying what you left out is 0. That to me seems like a safer course of action in terms of how to not screw something up. Anything else you wanted to add, either Vladimir or Erica, on this question, or others?
If you're adding the cluster mean times cluster mean quadratic term, what is the key thing you need to remember when interpreting it?
It's like a greatest hits collection today.
It could be a finger question.
It's definitely a finger question.
I'm trying to be vague for a hint. Would you just interpret it as is?
To interpret a quadratic slope as how it affects the linear slope, what do you got to do to it? That's the question.
I think you have to multiply by 2.
Yes,
Twice. Yes, twice linear slope.
Yep, because then it becomes the rate of acceleration.
I was just going to say, that sounds like a derivative question to me.
It exactly is, because the essentially what happens is if you take the first derivative of the function, that's your linear slope, and then at that point the 2 and the square term comes down in front. And so that's, yeah, if you remember derivatives, then this makes sense. If you don't, then think of it this way. An interaction affects each of its main effect slopes, right? If I have x by z, the interaction says that the effect of x changes by z and the effect of z changes by x. If you have a quadratic slope, though, it's one variable. You're missing like the other main effect. So I just think of it as it has to do that twice because there's no other variable in the problem to do it to. I don't know if that maths, but it makes sense to me. So, all right. Then what else? We got just a couple minutes left. Any other burning questions from folks?
a burning question, but just a statement. And I know Lisa saw this, but she told me to take it out. So when I was working with my data, and I actually was doing like a variable at a time at the various levels, what was kind of cool is seeing how the level 2, when you added how it impacted level 3. It made it a little bit higher, and I actually saw those along the way. It wasn't in the presentation, but I just wanted to say not only does it work between level 1 and level 2, you'll see between level 2 and level 3 that same sort of impact.
Yes, indeed. It doesn't always work that neatly, but like theoretically you can see it work if you have data that are simulated to behave themselves, so to speak. All right then, 142. This is it. Semester's over. I ran grades this morning. There's only one of you who has not submitted their peer review yet because it's not due until Tuesday, but I gave you your 5 points anyway because I wanted to get all the grades done. So you should be able to log into the homework portal and see where you're at. If anything is missing or looks wrong, let me know.
I said, do we want a class picture with everyone turning on their cameras and just having a screenshot?
We can do that. Is that, that used to be a thing in the Zoom. I don't see that button anymore. Let me see if I can find one.
You must select gallery. Is that what you're talking about?
He wants a picture, I think is what he was suggesting.
Ah, you can take pictures on Zoom. I didn't know that.
Mm-hmm. There's a button for it, but if I can just do a normal screen share. Yeah, I'm not seeing it. But all right, well, we'll just do normal screen share. Okay, everybody smile. Okay, I think I got you. Let me, I will save that and send it out over email. Just make sure I got it. Yep, and everybody's eyes are open. It's like a miracle. Of course, I'm not in it because I turned mine off. Do you want me in your picture? Okay, I'll turn it on. There I am. I truly hate having my picture taken, so you should just know that this is for you.
Thank you.
Okay, ready? Everybody smile. Okay. Let me try that again. Make sure I got everybody in here. Okay, I think we got everybody. Excellent. Thank you. So, thanks for being here. Thanks for showing up on the last day. Thanks for showing up the whole time. I really appreciate the effort that you put into this. I know this stuff isn't easy. I will say that you have earned the right to bother me. I'm leaving Iowa, but I'm not dead. So if you have multi-level modeling questions in the future that I can help with, please go ahead and reach out. If you're looking for examples of particular kinds of models, for instance, since we didn't get to go through all the various extensions, let me know. I can probably point you to some course materials. I don't know what I'm going to be teaching in the future. I'm teaching regression next semester as a starting point, and then we'll see after that. But my YouTube videos will live on. So I plan to keep them alive, and you can refer back to them as much as needed. So thank you. I hope everybody has a wonderful break. Let me know if you need anything, but I think we're done.
Thank you.
Are you posting the class you're teaching in the new school online too?
I think so. We will see.
Thank you.
All right. Thank you, everybody. Bye for one last time.
Thank you, Erica and Vladimir.
Yes, and thank you,
Thank you.
TAs.
Everyone.
We'll see you on
You, Vladimir.
Sunday, the party. Everybody should go.
Bye, folks.